Hello, my name is Anthony Gonzales, and I'm going to be presenting fascinating ways to approximate pi. So let's get right into it. So, what is pi? Depending on who you ask, you might get different answers. So, some might say that pi describes a ratio, or some might say that pi describes a circle. Some might even say that pi is what they had on Thanksgiving. But that's besides the point. Pi, by definition, pi is the ratio of a circle's circumference to its diameter, where the circumference is the distance around the circle and the diameter is the longest distance across the circle. So pi is special because no matter how the circle changes, the ratio stays the same. How do we obtain this value of pi though? Like, okay, it's a ratio, but how do we figure out like the value of pi? There are numerous ways to approximate pi, but we're going to be looking at the interesting and more unique methods. So we'll start by looking at the most well-known methods, so Archimedes' Ngon method and the graphing method. And then after that, we'll look at some more interesting methods that won't put you to sleep. Uh, we're going to look at the sliding block problem, the Buffon's needle problem, and the Diophantine approximation of pi. So starting with Archimedes' Ngon method, we have a hexagon with side length 1. So we're going to divide this into equal triangles, as we can see in the figure. And then we can see that each central angle here has a measure of 60 degrees. And that's because we have 360 degrees all around. So if we divide this into 6 pieces, then it's going to be 60 degrees for each of these. Now, if we look at just one triangle, so let's look at this triangle right here. We know that this is 60 degrees. And then in a triangle, the sum of all the angles is 180 degrees. And since this triangle has two equal sides, there are two equal angles as well. So all of the angles in this triangle has measure 60 degrees. Now we're going to look at just one triangle here. So this triangle is just pulled straight from here. Let's say it's just this triangle right here. We just pop it out, and now we're looking at just that individually. And remember, we're trying to find the area of this. So if we're looking at just this triangle, we can use the Pythagorean theorem to analyze it. The hypotenuse we can see is 1, and then the base is also 1. But we're going to split this in half, so now we have two right triangles. That way we can actually use the Pythagorean theorem. Now we have the base is 1/2, and the hypotenuse is 1. And then we can determine that this is √3/2 by using the Pythagorean theorem. Now, using the area of a triangle formula, which is 1/2 base times height, we can multiply all of our values together, and we get √3/8 for the area of this right triangle right here. If we want the area of this whole thing, we're going to multiply √3/8 times 2, and that's going to give us √3/4. And remember, this was just one part of this hexagon right here. So if we have, this is the area, we got the area of one triangle. We're going to multiply this by 6 to get the area of the whole hexagon. So multiplying by 6, we get 3√3/4, which is about equal to 2.598. Now we can see that this isn't a very good approximation of pi. So what Archimedes did was he added sides to the hexagon to increase the size of the hexagon. So now we're looking at maybe a 12gon, and if you determine the area of the 12gon, that'll give you a closer approximation to pi. You actually get that the area of the 12gon is 3. The reason this works is because when you are adding more sides, you are getting the sides closer and closer to the side of a circle. So if you keep on adding more and more, you're going to get closer to that circle, and that's going to get you closer to the area of the circle, which is supposed to be pi with a radius 1. The next method we're going to look at is the graphing method. So we have 5 circles of varying sizes on this graph. I guess it's not really a graph, it's just a figure, but we have 5 circles. We're going to use a string and a ruler to get rough measurements of the diameter and the circumference of each of the circles. So imagine you have your string and you have a ruler. You're going to go find the diameter, find that length, and then go around the circle, find the circumference, get that length. Then we're going to put those on a table. So for C1, 2, 3, 4, 5, we got these measurements here. Then we're going to plot these on a graph. So we're going to say that the diameter is the x values on the graph and the circumference is the y values on the graph. So graphing these, we get this graph right here. So the points seem to be somewhat linear. So we're going to try and find a slope between each point because we want to find a line of best fit. Actually, it's this way. Line of best fit that goes through those points there. So if we calculate the slope between each point, we get these values on the right-hand side. Then after we find the slope between each point, we want to find the average slope between all of the points. So to do this, we're going to add all of our slopes together and then divide by 4 because we had 4 total slopes. So adding all of those together and dividing by 4, we get 3.184, which is, I would say, pretty close to 3.14, which is what we know as pi. Okay. And next, we're going to move into a bit of a more difficult problem, the sliding blocks problem. So I'm going to start off by saying that this is an experiment with no resistance and perfect elasticity. And this will be more important in the next slide. But the problem is as follows. We have a 1 kilogram block sandwiched between a wall and a larger block. So that larger block is going to collide with a smaller block, and then it's going to hit the wall, and then it's going to come back, hit the bigger block, and then go back and forth until the larger block travels off and the smaller block can't hit the larger one anymore. So how many collisions should we expect to see? Given that this is a presentation on pi, I think you're going to see some of the numbers that involve pi. So let's look at a visualization. And this is where no resistance and perfect elasticity comes in, because if we had some sort of resistance or if we had any sort of elasticity, then the blocks that are sliding, there would be outside forces, and we don't want that in an experiment. So this is what it looks like. We can see up on the top right, the number of collisions lines up with the values of pi. Let's look at that one more time. I just think this is so cool. And there it is. So why does this work? Why does this happen? To get a better understanding, first we're going to introduce some formulas. So we're going to start with the velocity formula. So to determine the velocity after a block collides with another block, or if a block collides with the wall, to determine the velocity after collision, we're going to use the conservation of energy formula, which is on the screen there. And then to determine the momentum after a collision, we can use the conservation of momentum formula, which is also on the screen at the bottom. So looking at the energy equation, which we have that on the top left now of this figure, this is actually on a graph. This represents an ellipse. But since we're in the search of pi, we're going to try and make this a circle by changing some of these variables. So if we let y equal something different and x equal something different, that'll change our formula here, but we're going to get a perfect circle. So if we change y to this and x to this, now our new formula is 1/2 x squared plus y squared, which we know as a circle. So this represents our experiment, but how? So before we get into the first collision, we have to look at before anything happens. Before anything happens, we are going to be at the leftmost point of the circle. And this is because our x coordinate is negative. So it's actually on this side. So it's on the negative axis for the x, and the y coordinate is 0, which is where that red dot lies. That is before anything happens. Now, when the big block collides with the smaller block, what do we think is going to happen to that dot? It has to go somewhere on this circle, but how do we determine where on the circle it's going to end up? For that, we're going to use the conservation of momentum formula. Before and after the first collision, we know that this formula right here must remain constant. And there's a change of variables, so we're actually looking at this formula right here. We know that this must remain constant. We can see that this is actually the equation of a line, so we can find the slope of this line. The slope of this looks like this right here. It's a negative slope. So after the first collision, we know that the line, this is our slope. This is going to be after the first collision. So this dot could be anywhere over here as long as this slope is just like this. But the reason it ends up exactly where it's at is because we know that the slope must pass through our starting point right here. So that is why we have this line right here. Now the second collision. The first collision was when the big block hit the small block. That counts as one collision. The second collision will be when the small block bounces off the wall. So the speed doesn't change. It stays the same, but it goes from negative speed to positive speed. So we were going this way, and then we hit the wall. Now we're going this way. So we're going negative to positive. In the diagram, this corresponds to reflecting about the x-axis. So we were here, but now we're up here. So we went from a negative speed down here all the way up to a positive speed. Now, if we repeated this and we kept on plotting these points, we would see that we would have the same negative slope, but it would have to pass through that point. So our next point will be about here. Then we bounce off the wall again, and we reflect up this way. And then the negative slope happens again, and we continue. So now our picture looks like this. This will continue until the velocity of the smaller block is both positive and smaller than the velocity of the bigger block. And that's when the smaller block stops moving, which is going to be right here. So we can imagine what happens if we make the block that is colliding into the smaller block. If we make this block bigger, what do we think will happen? This is what it looks like. So if we increase the size of the block, this will increase the amount of collisions, which makes sense. But in our picture, we can see that the amount of collisions corresponds to the amount of points we have on this circle. Now, the full proof for this concept is pretty lengthy, and it got very difficult to understand, but I can see how at this point, we're going to start seeing the value of pi. As we saw in Archimedes, the closer you get to finding the area of a circle, the closer you are to evaluating pi. And here we can see that we are filling in this circle. So we would imagine that at some point we're going to start seeing numbers of pi. This is as far as I got with this problem, but it is interesting to this point nonetheless. So looking at the next problem, we have Buffon's needle. So the problem consists of a needle and a floor with some lines. So we have a floor with horizontal lines spaced 2 units apart. If we drop a needle of length 1 onto the floor, sometimes the needle intersects one of the lines on the floor, sometimes it doesn't. We'll repeat this several times. The question is, what is the probability that a randomly dropped needle will cross one of the horizontal lines? When I first looked this up, I thought it was going to be pi because this is a presentation about pi, but it's a little bit different. So what is the probability? To start this problem, we need to consider all of the ways that a needle can fall on the floor. So we're going to considering all the ways that the needle can fall on the floor, we have different vertical positions like this, but it can also fall at different angles. So we're going to consider all of the vertical positions and the angles. So it can fall here, or like this, or over here. So obviously there are a bunch of different ways that the needle can fall on the floor. Sure. we're going to compute the proportion at which the needles intersect a line. So let's create some variables. Looking at this picture, just to understand the problem a little better, these black lines at the top and the bottom are going to be our horizontal lines spaced 2 units apart. This blue line is going to be our needle. So we're going to focus on the midpoint of the needle right here because we know that the needle is length 1. So half of the needle, that midpoint, is going to be half the distance from each of these endpoints. Now we're going to define some things, so some variables. We have d is going to be the distance from the midpoint of the needle to the closest line. So since this line is closer, d is going to be this distance. If the needle was down here, then d would be the distance from the midpoint down to this line. So d can change, but we're going to call d, we're going to have d up here in our figure for the rest of this presentation. Now theta is going to be the angle of the needle relative to the horizontal lines. So we have theta here. We're going to imagine there's an angle right here, and that's going to be our angle theta. So for a given distance of the middle part of the needle, when will the needle intersect one of the lines? So that's going to actually depend on the angle that the needle makes. So we want to think that for a given distance of the middle part of the needle, the locus of points that could spin around as an angle. So we have this circle right here, which is going to be the locus of points, and it can spin around. So this needle, imagine it's spinning, that's all of the points that this needle is going to hit. So which angles will the needle intersect? We can use trig to figure this out. If we think of this needle, don't look at this bottom half of the needle, just look at the top half where it's above D. We have a hypotenuse, and then we have 2 legs. So we know that the hypotenuse is equal to 1/2 because that's half of the needle, which had a length of 1. We also know that this angle right here is theta. So we can determine that this leg, by using SOHCAHTOA, is 1/2 sine theta. So we can see that the needle crosses the line, and that line is this line up here, if and only if D is less than or equal to this value right here. So to interpret this better, we're going to look at the space of D and theta. So we drew a graph, or I guess a figure, but technically it is a graph because this is our line, 1/2 sine theta. This is what that line looks like. Now, the condition that the needle crosses is going to be this shaded region down here. And we can compute the probability by finding the area under this curve divided by the area of the whole thing. And that makes sense because the probability is going to be, it happens over everything. So this is the universal, everything happens, like all of the probabilities of anything happening is this whole rectangle. So the probability that it crosses is going to be this shaded region. So to determine the probability, like I said, we're going to do the area under the curve divided by the area under the area of the entire space. So for the area under the curve, we can use calculus, and we saw in this figure, we have our bounds are 0 to pi over 2. And the equation was 1/2 sine theta. So working this integral out, you get 1/2 as your answer. And then the area of the entire space is going to be length times width. And we get 1 times pi over 2, which is going to give us pi over 2. So now dividing, we get 1/2 divided by pi over 2 equals 1 over pi. So the probability that the needle will intersect a horizontal line is 1 over pi. So this actually gives us a numerical way to approximate pi. If you have hundreds of thousands of hours on your time, you can create this experiment, put some tape on the ground, space them maybe 2 inches apart, grab a needle, maybe not 2 inches, maybe 4 inches, and then grab a 2-inch needle, drop it on the floor a bunch of times, and record your outcomes. You should get that if you drop a needle on the floor with horizontal lines double the size, you repeat this experiment n times and count the number of intersections. So we're going to call the successes x. A success is going to be an intersection. So if you do that hundreds of thousands of times, the number of successes divided by the number of tosses will give you what we did before, this value of 1 over pi. So if you want to find pi, or if you want to approximate pi, the number of tosses divided by the number of successes will give you the value of pi. So when you have free time, go ahead and try this out. Now, the last thing that I'm going to talk about is the Diophantine approximation of pi. So this isn't like an experiment like the sliding block problem was, or like what we just looked at. It's more of just an observation. So to start off, a Diophantine approximation is the approximation of real numbers by rational numbers. So we have pi, which is a real number, and we want to find a rational number that is almost equal to pi. So we have that 22 over 7 is a Diophantine approximation of pi. That's because 22 over 7 equals 3.142, and then some other numbers, while pi equals 3.141. So 22 over 7 is almost equal to pi. So some people, I don't know who, maybe some maniacs, use 22 over 7 when they're doing some approximations. Maybe this was before calculators, but 22 over 7, if you need very rough estimate of pi, you can use 22 over 7. Now we can actually see that 22 over 7 is larger than pi, and just because I found this proof and I like it so much, I want to show the proof that 22 over 7 is greater than pi. So if we look, we can see some integrals and some weird stuff happening. On the left side here, we have 0. We have an inequality. We have 0 is less than this integral. Now this integral, we're going to look at this over here. So don't worry about the inequality. We're just going to look at the integral. First, we start by expanding this integral here, and we get this on the top. Sorry, we expand this polynomial. Now we're going to long divide, and that will give us this polynomial right here. And then after we compute the integral from 0 to 1, well, technically not 0 to 1 yet, but we just do the integration step, we get this. Then we can compute it from 0 to 1, and we get these numbers and these numbers. But you'll notice that arctangent of x appears in here, and that's how we get the value of pi. Arctangent x comes from this 4 over 1 plus x squared. If we take out this -4, now we have 1 over 1 plus x squared, and the integral of 1 over 1 plus x squared is arctangent of x. So then they just brought that 4 back in, and now we have this. If we have the arctangent of 1, we get pi over 4, and the arctangent of 0 is 0. So that's where the pi comes in, which I think is super neat. So once you calculate all this, everything on the right side is 0. On the left side, these fractions are going to add up to 22 over 7, and we're going to subtract by 4 pi over 4, which is just subtract by pi. So then we get 22 over 7 minus pi. Now, we know that this integral is greater than 0. So we can write that 22 over 7 is greater than pi, which I just think is so cool. Yeah, overall, we talked about what pi is. We learned that it's a ratio. We also learned that it's what some people eat on Thanksgiving. So there's that. But it's important. It's everywhere, which I think is crazy. We saw in the sliding block problem, the number of collisions came out to be some value of pi. We saw that in Buffon's needle, it's in probability problems. We just saw a Diophantine approximation, which isn't necessarily an experiment, but it was someone that maybe wanted a rough estimation of pi, and they use that for maybe their mental math. So pi is everywhere. Uh, there's so many ways to approximate it. I'm going to be doing this on my free time because this is just such a fun topic to learn about. So I hope you enjoyed my presentation. I will see you all next semester. Thank you.